Lesson 1.9 is on patterns, equations, and graphs. If you look at page 61, the top of the page, they have a table that shows a relationship between the number of kites in an arrangement and the total number of ribbons on the kite's tails. Describe the pattern in the table and how many kites could you make with 275 ribbons. Okay, so if we look at the information here, one thing we can do is figure out what is the pattern of the total number of ribbons. So the ribbons, we went from 5 to 10 to 15 to 20. So we can see the number of ribbons is increasing by 5 every time that we have one more kite. What's the relationship between the number of kites and the total number of ribbons in each arrangement? So we have 1 kite, 5 ribbons, 2 kites, 10 ribbons, 3 kites, 15, 4 kites, 20. So depending how we look at this, we could say take the number of kites, multiply by 5, gives you the number of ribbons, or you could go the other direction if you wanted also. So for that, we could talk about, the book doesn't really ask us to do this too much here, but we could come up with an equation of the ribbons equals 5 times the number of kites or something like that. I guess they did ask a question of how many kites could you make with 275 ribbons. So that would be one thing then we could figure out, either using the equation or just figuring it out a different way. So one way we mentioned a minute ago, if you take the number of ribbons and divide by 5, that gives you the number of kites. So that would be 55 kites. Another way of doing it, if we use this equation, we could just substitute into the equation and we could say we've got 275 ribbons, and then to solve for the kites we would divide by 5. Okay, so there's different ways we can do this and still get the same answer. So one thing, if you look a little further down the page here, it talks about a solution of an equation with 2 variables. So in a solution of an equation with 2 variables, x and y is an ordered pair that makes the solution true, or makes the equation true. So if we can put a pair x and y, certain numbers, into the equation and it works, then it's a solution. If it doesn't work, then it's not a solution. So if you look at problem 1, they're asking, is 310 a solution of this equation? So all we're going to do is substitute into the equation. One thing you may want to do is just mark which one's x and which one's y. Okay, this is an ordered pair, like if we were graphing a point. So the 3 is the x, the 10 is the y. Substitute those into the equation and see if it works. So if you do that, you got 10 equals 4 times 3. 4 times 3 is 12, not 10. So those are not equal, so 310 is not a solution of that equation. And kind of going back to what we talked about before, basically that tells us that that line, if we would draw a line y equals 4x, it doesn't go through the point 310, would be one way of thinking about that. So if you look at the got it 1, we're looking at some other options for y equals 4x to see if any of these are solutions to this equation. So once again, it's the y equals 4x. So part A, we put a 5 in place of the x, we put a 20 in place of the y, and then we're seeing if these are equal. So when we do this, 4 times 5 is 20. 20 equals 20. So since that came out correct with the correct statement, we could say yes, that ordered pair is a solution of that equation. So we'll look at part B. We're still going off that same equation. Highly recommend you write down the equation, and it only takes a couple seconds to put the x and y above your numbers there just to make sure you put them in the right spots in your equation. So we substitute in, we got negative 20 equals 4 times negative 5. I guess we'll put a question mark because we're seeing if these are equal or not. And that works as well, so that is a solution as well. And then part C, same idea. So for this one, starting with our equation again, negative 5 for y, negative 20 for x. That'll be negative 80. Negative 80 is not equal to negative 5, so that is not a solution of that equation. On the next page, it talks about how we can represent a relationship between two variables several different ways. We can use tables, we can use equations, we can use graphs. So if you look at problem 2, both Carrie and her sister Kim were born on October 25th, but Kim was born 2 years before Carrie. How can you represent the relationship between Carrie's age and Kim's age in different ways? So one way they did this, they made a table. They said, well, if the one girl is 2 years older than the other, if one was 1, the other one would be 3. If one was 2, the other one would be 4, and so on. Another way we could do, which the table might be helpful in creating this, would be writing an equation. So if we say, maybe we'll say let x represent Carrie's age and let y represent Kim's age. And then if we think about it, Kim is always 2 years older, so we could say y equals x plus 2 would be an equation. X equals y minus 2 would work also, but usually what we're going to do, especially as we get into graphing, we're going to usually have y equals something. Okay, having the y by itself is going to be valuable for us to have. And then what we can do from there is we could draw a graph. So we could graph the points, basically graphing the points in the table where these are our x coordinates and these are our y coordinates. Or you could go off your equation and come up with points and then graph those. We are going to stay in the first quadrant here because nobody's going to have a negative age, but okay. And then if you look over to the side here, it says, why does it make sense to connect the points on the graph? A person's age can be any positive real number, so the ages are always 2 years apart. So every point on the line makes sense. Okay, so for example, you know, if we're looking at right here, we could say that Carrie is 2.5 years old and Kim is 4.5 years old. Okay, they could be part of a year old, so we connect the dots. Some cases, in between points don't make sense. Like if we're buying pizzas at the store, they're not going to let us buy 3 1/4 pizzas. Okay, so in that case, we would have what's called a discrete function where we just have dots. This is called a continuous function because the points just keep going. They just connect continuously. So if we look at the Got It 2 Part A, Will runs 6 laps before Megan joins him at the track. They then run together at the same pace. How can you represent the relationship between the number of laps Will runs and the number of laps Megan runs in different ways? Use a table, an equation, and a graph. Okay, so they want all three of the things here. So starting with the table is probably a good idea anyway. Okay, so, we could put a title here, Megan and Will's laps. And then if you think about it, Will runs 6 laps before Megan joins him. So we could start out with, Will's run 6 and Megan hasn't run any. And then after that, they're running at the same pace. So that would be 1 and 7, 2 and 8, 3 and 9. Just keep adding 1 to their laps each time there. So that would be a table. An equation, if we just make Megan be an X and Will be Y, normally we do our equation Y equals something. So just think about, we could think about how do we get from the X to the Y. So how do we go from 0 to 6, 1 to 7, 2 to 8, 3 to 9? So the numbers are getting bigger, so we're probably going to be either adding or multiplying. And on this one, you might notice we would be adding. Here's kind of a clue that we're not going to be multiplying. Is, if you go from 0 to 6, 0 times anything is going to be 0. So that would be an indication there's addition. And it's possible we could have equations that involve both addition and multiplication, or some combination of different operations. Okay, so this would be an equation, and then for the graph, we could just graph these points, graph the points 0, 6, 1, 7, 2, 8, and 3, 9. Okay, and then we can draw a line. We can connect the points because they could have run part of a lap at any certain point in time. When you graph that, make sure you label the x-axis as Megan's laps, the y-axis as Will's laps, and then just draw a straight line. So if we look on the next page, it talks about inductive reasoning. Inductive reasoning basically is making a conclusion based on a pattern. So we look at the pattern, and then based off of that, we come up with a conclusion. So on problem 3, they have a table that shows a relationship between the number of blue tiles and total number of tiles in each figure. Extend the pattern. What's the total number of tiles in a figure with 8 blue tiles? Okay, so if we look at this, we can see if we had 1 blue tile, we had 9 total tiles. 2 blue tiles, 18, and so on. Okay, so there's different ways we could do this. One way of doing this, what the book did, is they graphed the points that they had up to that point, and they noticed that made a straight line. So they said, well, let's just extend that line out until we get to 8 blue tiles, and then let's see how many total tiles that is. And they came up with 72. So that works. Another way of doing this would be making an equation. If you'll notice that the total number of tiles is always 9 times more than the number of blue tiles. So y equals 9x. So we just do 9 times 8 would be 72. Another way the book didn't mention would be just extending the table. So we could say, well, if we have one more blue tile, that's 9 more tiles. If we have one more, that's 9 more tiles. If we have one more, that's 9 more tiles. And then we could get the 72 that way also. Okay, obviously if we were wanting for like 50 blue tiles, we wouldn't want to extend the table. That's not a very efficient way, but if we're halfway close, that would be another option as well. So if you look at the bottom of the page, they want us to make a table showing the number of orange tiles and the total number of tiles, and then how many tiles in all will be in the figure with 24 orange tiles. So this one, we're looking at the orange tiles compared to the total. So the first figure, if you go back and look at that, first figure, we've got 4 orange tiles and 9 total tiles. So the second one, we've got 8 orange tiles and 18 total. The third one, we'd have 12 and 27. Okay, and that's probably good enough if we're doing a table here. If we want 24 orange tiles, we could just keep going until we get to that point. Another way we could do this is we could figure out a pattern. Now this one, the pattern's not quite as simple as some of the others that we've looked at. So you might look at this and you might say, well, it's getting bigger. The question is, how is it getting bigger? So you could say, well, maybe they're adding. Well, 4 plus 5 is 9. 8 plus 5 would be 13, not 18. So they're not just adding 5. Maybe they're multiplying by something. Well, to figure out what they're multiplying by, we could take the bigger number divided by the smaller number, 9 divided by 4, which would be 2.25, or you could just leave it as 9/4. See if that works with the second one. If we have 8 and we multiply that by 9/4, you can reduce that and you get 18. You do the third one, you got 27 times 9/4. I'm sorry, you got 12 times 9/4, starting in the wrong spot there, and you would get 27. So that pattern does work. So that tells us that y is equal to 9/4 times x would be an equation that we could use. And then for 24 orange tiles, remember the orange tiles was our x, so we could do 24 times 9/4 times 24, and if you reduce that, that would be 54 total tiles. Okay, like I said, you could just extend the table out if you wanted to and figure it out that way. So we'll look at the lesson check number 7. Which of those points are solutions of y equals x plus 2? And what is the pattern in the solutions of y equals x plus 2? So basically we're going to take those points and we're going to substitute into the equation and see if it works or not. So first we've got 3, 5. We put a 3 in for x. We put a 5 in for y, and then we see if that works. So if we do that, 5 equals 5, so that works. Next one, we put a 4 in for x and a 6 in for y. So 6 equals 6, so that works. 5, 7. 7 equals 7, that works. And then the last one, 6, 8. So 8 equals 8, so that works. So they actually all work. And then it says, what is a pattern in the solutions? Basically, if you'll notice, just the y values are always 2 more than the x values. The y values are 2 more than the x values. So this gives you an idea of how to work with patterns, equations, and graphs. Have a good day.